Okay, I would normally thank the organizers, but I noticed that my name is on the organizers list, so I probably shouldn't. I don't know if you'll thank me either after my talk. So this talk is actually a hybrid talk. I had originally decided to just give a talk on some results, new results in active hydrodynamics, but in the course of this meeting, I realized that the general framework for active matter dynamics is worth re-elucidating in a way that you'll see. That's where I am. I was there for the past about 4.5 years until recently, and I'm still affiliated with TIFR as an adjunct professor, and this is who supports me. Okay, so my talk has a simple structure. I'll outline, I'll motivate why we want to study active matter very briefly. I don't think I need to this crowd. And then I'll tell you a sort of a demystification of active dynamics, starting from equilibrium Langevin equations. I'll explicitly construct some examples of equations of motion using this approach. The results will not be new, but it's nice to see they follow that way. Then I'll specifically take up the case of the hydrodynamics of active fluids with momentum conservation and study how you go from 3D bulk hydrodynamics to the dynamics of a two-dimensional confined system with incompressibility in two cases, polar and apolar. This is unpublished work, and then I'll summarize. Yeah. Okay, so as at this point we have all understood pretty well, when we talk about active particles, what we mean is that each particle is in contact with some kind of fuel source. It directly gets free energy and has the machinery to do something with it. It'll be lovely to do all the stuff that I have here in gray, but I'm content at the moment with only doing this part. And active matter or active condensed matter is collections of such particles. And you can, of course, take the point of view that the particles don't matter. You're just going to study system directly, coarse-grained. But as we've again seen in this workshop, a lot is to be learned by starting with particles. Most of what I say today won't start with particles. But if you accept this broad definition, then not only these obvious examples of active matter with large-scale real living things and components drawn from living things constitute active matter, but various artificial realizations, such as the ones that Ajay talked about and other people mentioned, and even, rats, I'm just not used to this. Even completely exotic systems, like basically if you take any two-dimensional system and connect it, flank it with two three-dimensional baths, which are held under thermodynamically different conditions, so that you're pumping energy through this two-dimensional system, the effective dynamics in that two-dimensional system should lie in the same framework, in the same family as the kinds of equations we're writing down. And this is not just my pipe dream. In fact, the so-called zero resistance state of two-dimensional electron gases has been analyzed using slight modifications of Toner 2 flocking equations. So if somebody asks you, if your quantum friends ask you whether this stuff is really important, you can say, yes, it is, because it even comes up in these contexts. Okay, and clearly the common feature is just that you're directly driving the constituent degrees of freedom, which dissipate power and do something. Okay, so that's the very general introduction. And again, to the students in the audience, just to remind you that the whole point about these systems is that they're open, they are subject to a constant maintained throughput of power, and they're, in a fundamental sense, you're studying systems which are held under conditions where time reversal invariance is broken. Okay, so I think I want to be on this side. Yeah. What I want to do is I want to spend about a third to a half the talk re-reminding everybody of how you build equations of motion for active matter, because I want to point out that there's nothing particularly exotic about what we're doing there. Okay, so the idea is the following. First, a motivating remark is that people with my kind of training, when given a problem in a system far from equilibrium, will say, look, I know how to write down the equations for this system, because what I'll do is I'll respect all the spatial symmetries of the system, I'll respect all the conservation laws, and by pure thought, I'll just write down the equations saying that anything that you haven't explicitly forbidden is allowed. And I know how to do that. In fact, that is really how we started working in this game. Okay, so there is this general idea that whenever you take a system that's out of equilibrium or active or whatever, there are going to be new terms that are ruled out in the equilibrium dynamics. People use words like cannot be derived from a free energy or things of that sort. Those are all somewhat imprecise terms. But basically what it means is terms that you know you can't write down for the dynamics around the very special steady state known as thermal equilibrium are all of a sudden allowed. But what I want to do is to spend a few minutes, actually not even a few minutes, a little more than a few minutes, showing how this comes about in a general framework. This is spelled out in some detail in a short article in connection with a talk I gave at StatFizz. And it really corresponds to a Langevin equation version of what the Curie, the Paris people, the framework they use by writing down dissipation functions. Okay. General idea is very simple. You have a physical system which has some spatial directions, which I've just given you, of which I've given you one and called it Q. You have a chemical direction. What I mean by that is that if you move in that direction, it means you've eaten more and more and more and more and more fuel. Okay, so X is how much fuel you've consumed. And clearly the idea is that an active system or a motorized or powered system is something in which direction is direction through a mobility which has off-diagonal components. Okay. So what I'll do is I'll use this idea within linear irreversible thermodynamics to build the equations of motion. But as I said, the only difference really with the way the Curie folks do it is that I'll write down Langevin equations for all the variables, including the chemistry. Okay, and this driving force in the chemical direction you can think of as a maintained, as the chemical potential difference between reactants and products. Okay. You can also feel free to stop me at any time. I'm going to be slightly pedagogical. Okay, now this is a slightly ugly looking slide, but the idea is the following. As a more paradigmatic example, let me take a system which has some coordinate-like degrees of freedom, Q, which are even under time reversal, some momentum-like degrees of freedom, P, which are odd under time reversal, and an additional degree of freedom, which we already gave it away, is the number of fuel molecules consumed. Okay, so progressing in the X direction simply means consuming more and more fuel. And now imagine, at the moment, don't think of X as a fuel. Just think of it as some chemical coordinate, and imagine that you'll first consider a case where the chemistry is at equilibrium. Okay. When I say at equilibrium, what it means is that the chemical coordinate, of course, if it's at equilibrium, since, let me just say it by the equations, okay? So at the moment, don't even think of X as a chemistry variable, just think of it as some other dynamical variable, position-like, okay? So imagine you're going to write down the effective statistical dynamics at thermal equilibrium for three variables, Q, T, and X. And let's say these are already coarse-grained variables, so the dynamics of Q and T isn't microscopic Hamiltonian dynamics. So even Q's equation of motion can not only have reversible dynamics with respect to an effective Hamiltonian, but also downhill dynamics in that energy and a noise. So Q dot is H over dP plus damping and noise. And let's, for the time being, purely formally, just to make everything look really like mechanics, let's introduce a momentum. Let's introduce a momentum conjugate to X. At the moment, for formal purposes, I'll do away with it in 1 minute. So then I'll have an equation for P, which is P dot is minus dH over dQ, and an equation for pi, pi dot is minus dH over dx. H is to be viewed as an effective Hamiltonian, which means that it's really defined by taking the log of the steady state distribution function and insisting that it is actually equilibrium. In other words, it's actually that object that enters the detailed balance relation. Okay, so that's what I really mean by X. I want to insist on that from this stage. And supposing the damping matrix gamma with components gamma 1, 1, gamma 1, 2, gamma 2, 1, gamma 2, 2 isn't diagonal. So gamma 1, 2 and gamma 2, 1 are non-zero. Then the dampings of P and pi will in general get contributions from each other, right? P dot will get a contribution from dH over d pi, and pi dot will get a contribution from dH over d. Okay. So this is a sort of complete Langevin, and there are corresponding noises, eta and psi. And because this matrix has off-diagonal components, eta and psi have cross correlation. I should also point out one more technical note, which is that I would, unless gamma 1, 2 depends on at least the spatial coordinate in the problem, all of this is not interesting, right? Because then you won't get anything new in the dynamics, right? Because I have wisely kept the momentum degree of freedom, the fact that gamma 1, 2 depends on Q does not introduce stochastic ambiguities, because I've kept, at present at least, I've kept the inertia. So I don't have to worry about Ito and Stochanovich at this stage of the game. For those who like that kind of thing, it's a convenience. Okay? All right. So that's equilibrium dynamics. So what do I want to do with this? First, I should have done this. Yeah. So these, as I said, are off-diagonal Onzaga coefficients. And so within the linear reversible thermodynamics, gamma 1, 2 is equal to gamma 2, 1, which I should have said. And now what I want to do is, first of all, since x ultimately is going to be this chemical coordinate, I don't want to worry about trying to define what I mean by an inertia or a momentum for it. So let me do away with pi dot altogether. I'm allowed to do that. Let me start, instead of dH over d pi, let me just use x dot everywhere. And so I have equations of motion of this form. So the Q equation, the P equation in which the damping of P depends on the chemical velocity, the chemical equation, which I have written in this form, damping times chemical velocity plus physical velocity equals force, equals chemical force and noise. Okay, so we're still at equilibrium. Okay, and so what I want to do in order to rewrite this in a language where x dot doesn't appear is simply use the x equation to get rid of x dot from here in favor of dH over dx. Because dH over dx, what is dH over dx? It's how much h changes if you consume one x. So it is delta mu. It is the chemical potential difference between reactant and product. Okay. So what I want to do is therefore rewrite this. Shuffle my slides. No, I'm not. Yeah. So I've eliminated x dot in favor of this guy by solving this equation for x dot in terms of dH over dx, dH over dP, and the noise. Okay. Let's actually remind ourselves of what that means. What this means is that you get noise once you carry out this elimination of x dot. You will have a contribution from the chemical noise. You will have So you'll get a modification of the damping, you'll get a modification of the noise, and you'll get a change in the systematic force. So the momentum equation, after I carry out this elimination, has a damping term with a coefficient gamma, which is the original damping minus this combination. The noise in the same equation is a combination of this noise and this noise, in this form. The x equation, now rewritten by dividing through by gamma 2, which again I can do with impunity because I have not worried about gamma 2 depending on any of the coordinates, is a Langevin equation for a chemical coordinate driven not only by the chemical force but also by the physical velocity. Okay, and so in this version of the dynamics, you notice that the coupling of P to X and the corresponding coupling of X to P is now through an anti-symmetric combination. You get a minus gamma 1 2 here and a plus gamma 1 2 there. So all of a sudden, by throwing away the inertia for X and writing as first order dynamics for X, we get a formal Poisson bracket-like relation between the chemical coordinate x and the physical momentum-like variable p. These two equations taken by themselves are the effective dynamical equations for the coordinate and the momentum in the problem. Now that the damping in the x equation is purely diagonal, this noise and this noise should have no correlation with each other, and you can check that they don't. You can check also that this effective noise, which is the original noise minus plus something contribution to the chemistry, and this effective damping, which is the original damping plus contributions from gamma 1, 2, you can easily check that they again satisfy a fluctuation dissipation relation of the second kind. The autocorrelation of this F will be KT times this guy. Okay? And still, as I said, because I've got a P dot, I don't worry about the Q, the fact it's a Q-dependent noise. Okay? And X has its dynamics. So at the moment, this is still the equilibrium dynamics of Q, T, and X. Maybe I'm laboring the obvious, but I found this entertaining, so I'm going to inflict it on you. Okay, so now let's just change names. Let's call dH over dx, let's call it delta mu, and replace these dh over dx's by delta mu. And let's hold that delta mu at a non-zero constant value. Okay. So then what you have, if you include the chemistry, is you have an equation of motion for Q and P. The P equation of motion now has, remember, delta mu is now just a number, which is what I'm holding in my hand. It's the maintained chemical potential difference between reactants and products. And I get a term gamma 1, 2 of Q. I haven't said what gamma 1, 2 of Q is, but obviously whatever it is some function which is allowed by the symmetries of the system. Okay? So you get an equation for P with terms that you wouldn't normally have guessed at. In background, you also have the X dynamics in the presence of a constant driving force still taking place. The chemistry is proceeding coupled to the physical velocity, fluctuating because of its noise, and driven on average systematically in one direction. So if you keep delta mu constant, what you have is this combination of equations of motion. Okay? And so at the moment, let's relegate the chemical dynamics to background and just look at the physical part of the dynamics. You have a pair of equations of motion for Q and P. Nothing much, because of the particular class of models I started with, nothing very dramatic has happened, nothing really significant has happened to the Q equation at all. The P dynamics has this guy. And this guy, gamma 1, 2 of Q, is what we like to call new terms not permitted in the equilibrium problem. Okay? So what's happened really is you've done something funny. You've worked in linear, in a sort of linear response picture, and then what you do is you hold how far you are out of equilibrium constant, but always pretend it's constant but not too big. If you, for example, in general, ratios of forward and backward processes should have exponentials of delta mu minus 1 or something. If you like, delta mu is just the first term in such an if you expand those exponentials. Okay? So what this says is that active system Langevin equations are just the Langevin equations you know and love, in which you introduced some other variable which you don't directly see. It could be, something, a forcing perpendicular to the directions you're seeing, or a forcing in a chemical direction. And that ultimately, if there is a chemomechanical coupling, if that variable couples to the variables you are monitoring through a dependence of the off-diagonal kinetic coefficient on the coordinate, you end up getting this form. And in general, clearly, since gamma 1, 2 wasn't terribly, gamma 1, 2 is going to be constrained by the spatial symmetry of the system, but it still leaves a very large class of possible terms available. See, supposing Q was not a microscopic coordinate, it was a coarse-grained variable, let us say it's the orientation field of some system or a polymer conformation or something, then it's going to have its damping and its noise. I mean, supposing you had a coordinate degree of a polymer conformation and a velocity field, you're writing down the dynamics of that system. Then there'll be a local Rouse type damping and a local noise corresponding to that. So in almost any problem other than just looking at one particle moving in a potential, you will have this. In any coarse-grained description, even if Q is a coordinate-like rate freedom. So if you're writing down pneumatic hydrodynamics, for example, you'll have it. So you shouldn't think of Q as one coordinate and P as one momentum. You can think there's any number of components or fields for that matter. So I mean, if you write, for instance, if you wrote down time-dependent Ginzburg-Landau for an order parameter, you have a damping of that sort. So you should view it in that spirit. Why should you? Because supposing you're writing on the hydrodynamics of a liquid crystalline system, you've got an orientational order parameter and you've got a velocity field. And depending on the range of wave numbers you're looking at, you could want to keep inertia or not want to keep inertia. That's up to you. Right? So, of course, I'm really keeping P so that I can avoid until the very last minute any Ito-Stoyanovich troubles. That's one of the reasons I'm keeping it. But you have to allow me to do that. Okay, so this is what, and I take this as a sort of permanent license hereafter not to have to do derivations of this sort, but just write down equations by pure thought the way I learned at my mother's knee. Yes. So the effect of X has entered by modifying the damping and modifying the noise. Yeah. Of course, all of this is being done in a kind of make-believe world where we think that the bath is unaffected. Clearly, if you take an extreme system like agitated granular matter or something, the thermal bath has nothing to do with it. There's a whole other bath which is created by the shaking. But this is okay for systems in which there's a good scale separation, in which the noise is coming from molecular scale physics and the driving is coming from something somewhat larger. So actually, there's some caveats. I mean, this whole story is a little dear to my heart, so let me dwell on it a little bit more. I indulged in some sleight of hand. I eliminated X. H originally was a function of Q, P, and X. I can only eliminate X if terms like del H over del P and del H over del Q didn't have any X in them. So I'm assuming that X enters trivially, additively in H. It'll be interesting to know what happens if something more than that happens. I haven't worried about it. Okay. So I said there's actually nothing new in this, but to me this was a clarifying exercise. It bothered me, so I thought maybe some of the faithful would be interested. All right. So I'm going to inflict this on you for a little bit longer before I go to a specific example. Really? Okay. So, okay, in particular, you can now also go over to a no inertia version by throwing P dot. Then you have to worry a little bit. Yeah, because gamma contains gamma 1, 2. So I've rather cavalierly divided through by gamma and written an effective equation for maybe I'm still okay. It's still okay. So if I eliminate, no. So I've written this equation down, but there is a slight issue because I've done an adiabatic elimination without sort of getting all clearances. So if I want to go to a purely no inertia equation of motion, I could have to worry. So just full disclosure. Okay. All right. So the point is, I've got this dynamics. I can forget about P dot and say that where I see dH over dP, I'll replace it by what I get by throwing away P dot here. I'll get an effective dynamics in terms of Q alone. Again, if Q is a single scalar variable and just a function of time, then obviously I can redefine my energy function, absorb this into that, etc., or redefine my damping or something like that. But in general, if Q is even two components, then unless gamma 1, 2 miraculously happens to be a gradient or something, unless this whole combination happens to be a gradient, even then it's going to be different from equilibrium dynamics. And certainly if it's a field, it will be. So let's use this approach. So I hope I've convinced you. At this point, I hope to, I better stop, I better move fast now. Okay, so for example, you can take any of your favorite problems. Supposing Q is the height field of an interface, then you will get whatever dynamics you would have had at equilibrium plus a gamma 1, 2 term. And you just say that, well, this gamma 1, 2 term can, and let's say the interface, it's an out of equilibrium system, and let's say the interface does not have inversion symmetry, but is translation invariant, then the simplest terms you can write down here are constant plus grad h squared, so you get the KPZ equation. Supposing Q was the vector orientation field of a bunch of self-propelled particles, then again, you could write down an equilibrium dynamics for those particles with some energy function and the corresponding noise, and then say there's a gamma 1, 2. That gamma 1, 2 has got to be a vector. So it can either be a polynomial in the orientation field, or it can be all contractions of W grad W which give you a vector. So W dot grad W or W, three possible contractions. So the Toner 2 nonlinearities emerge, obviously. If Q is the density field of a collection of active particles, then let's say you've got a dynamics where the density diffuses, has a noise, and has this, my favorite gamma 1, 2 term. Then again, I have to write down the minimal gamma 1, 2 that can conserve number and write down allowed coupling. So immediately a term like del dot W, where W is the orientation field, the polar orientation field, springs up. So the fact that the orientation advects itself, the fact that the orientation is a current comes out this way. And so the only place where, so in other words, the orientation field by itself is still an orientation field. It hasn't broken time, its time reversal properties are what they always were. The breaking of time reversal is done because of the delta mu in front of those terms. Okay, and you can go on, you can do this for apolar systems and get terms with 2 grads contracted on Q. You can do it for a full active fluid with an orientation field, a hydrodynamic momentum density. You can write down the dynamics of such a system with reversible and dissipative terms and noise. And returning to my theme, gamma 1, 2, and gamma 1, 2 has to be the simplest vector you can write down consistent with momentum conservation. So you can write down things involving a divergence of Q, or if there's a polar order parameter, you can introduce terms with 2 grads on W. So everything you wanted actually fits into this framework. It's not terribly surprising, but it's satisfying. Okay, so active stresses come naturally out of it. Okay, and so you get liquid crystal hydrodynamics with active stresses. And so that brings me to the rest of my talk, which is applying these ideas. So this is a very old story, so I won't repeat it in any detail at all. There are many properties of bulk. One of the most sort of conspicuous properties of a bulk-oriented active fluid is that it's spontaneously unstable. And the question is, what happens when you confine that? So a very simple-minded picture would be, I had my bulk system. I've now put it between 2 plates separated by a distance b. The active stresses give me a term, in these confining conditions, the active stresses in the effective equation of motion for the orientation field give me a term which, if I choose my definitions and directions correct, is always unstable either in splay or in bend. And under these confined conditions, if I do a very simple-minded treatment like this, I'll find that frank elasticity competes with this instability. And so under these circumstances, for low enough activity, the system is unstable. But if I crank up the activity large enough, basically, if I make the activity, which has units of stress larger than the Frank constant divided by the gap squared, then I should go unstable. So the question is that really all that happens? I've got a bulk active system, which in the infinite size limit is always unstable. I confine between 2 plates. Confinement restricts the instability. But if I crank up activity strongly enough, it will go unstable. So I'll discuss that question. I'll discuss another question, which is what happens. So the description so far didn't worry about the polarity in this last part. What happens is there a special interesting difference between polar and apolar systems? So let me spend about 5 minutes each. The way you do this is start with the bulk 3-dimensional active hydrodynamics. And the question you want to ask is a confined 2D, 3D system under confinement the same as a 2D dry system without momentum conservation? Now, this issue has been sorted out largely by other groups, but I just wanted to spend a few minutes on it because there were some things that weren't quite right in those treatments. So here's a side view of a confined polar active fluid. Let's say the boundary conditions are like that, and let's say the system settles down into a state with a polarity in that direction, viewed from the side like that. No, so this is sorry, excuse me. This is the side view of both, yeah. Let's work out the effective 2-dimensional dynamics by solving the Stokes equation, okay? So you have a 3D dynamics, you average over the z direction, and remember I said that there are active stresses proportional to the velocity. Remember I said there are terms in the velocity equation proportional to 2 derivatives on the polar order parameter. There are similarly terms in the polarization equation proportional to 2 derivatives on the velocity. And this is wrong. This should be del squared p. Right? But basically, when you carry out this elimination, you get an effective dynamics where the polar order parameter couples to the velocity and relaxes through energetic and other approaches. The velocity couples to the polarization. And now and it's still, the 3D incompressible system is now a 2D incompressible system. So the two-dimensional velocity field has incompressibility. Solve for the velocity, stick it in here, and you get the effective dynamics of the orientation field described in terms of an angle variable, is actually has a very curious form. It says the angle variable has a dynamics which is wave number independent and depends only on the direction of wave vector. So this is interesting because it means that even though it's a broken symmetry variable, and even though you've sort of suppressed the hydrodynamic interaction by confinement, you still end up getting long-range effects because of the incompressibility constraint. And that gives you a relaxation of the angle variable, which has the same sign in all directions, with a coefficient which comes from the activity. Okay. Now you can add a noise to this problem, and what you'll find, as Brotto and company remarked, is that the orientational fluctuations are modest, the density fluctuations are, so that means that long-range order is not disrupted by thermal fluctuations at all. The only thing I think that these guys didn't get quite right is that I think they argued that somehow there's a range of directions in which the system can be unstable. What really happens is that depending on the sign of this activity coefficient, it's either always unstable or always stable. And it's always super unstable or always super stable. Okay? That's for the polar case. Let's discuss the apolar case in the remaining 8 minutes and 18 seconds. Okay, so I have an apolar system. So let's go back first to the dry apolar case. Okay, let's just take a simple picture. I've got these headless particles. I've just used this slide to define the angle field theta in terms of which I'll work. One of the known properties of orientable active fluids in the apolar case is that if you have a bend or a splay, that gives rise to motion. That is this velocity proportional to the divergence of Q that I think Masaki talked about and Julia talked about. Okay, so curvature produces flow. And this was basically behind that original instability that I told you about in bulk, which naively it looked like if you put it under confinement should always also go unstable if you crank up the activity high enough. Now, this is what I said earlier. Okay, if you, however, take the equations of motion, now this is a ferociously technical slide. Angle field couples to velocity gradients and relaxes. Velocity field determined by pressure gradients, passive stresses, and active stresses. The passive stresses come from the energy function for the problem. The active stresses, basically through a generalization of this idea, come from terms that say, let's go back to this picture. This picture says that a bend or a splay in this picture, so if you have a curvature like this or a curvature like this, in this cartoon, I've argued that if a splay gives you movement in that direction, a bend should go, the arrow's lost its head, a bend should give you movement in that direction. That would amount to saying that V is proportional to div Q, which means that Vx is proportional to the y derivative of theta and Vy to the x derivative of theta, with, in this description, the same coefficient. Okay? Same coefficient there. However, there's no particular reason for those to be the same. You can take the following point of view that really, for example, I could say that V has a bit proportional to, V is something times div Q plus something else times Q div Q, right? Just like you do in elasticity, you can have a 2-activity constant rather than a 1-activity constant, active dynamic. In this language, that amounts to saying that the active forcing has, let's say the x component has something times d theta over dy, the y component something times d theta over dx, but these two coefficients don't have to be the same, which here has been written by having a zeta 1 plus zeta 2 and a zeta 1 minus zeta 2. Turns out, you can even derive that from horribly technical arguments in 3 dimensions, which I will not get into, except people can catch me afterwards. The result of this is that you can, in the space of the ratio of those two coefficients, these guys, and the flow coupling parameter, these guys, you can find a whole zone, a whole region in parameter space in which you can crank up the activity as high as you like, and you will not enter an instability. So I think that's all I wanted to say. Maybe I spoke too fast, I don't know. Yes, so I think I'll stop there. So my talk had two somewhat disparate parts. One was a slightly different way of looking at active dynamics. Maybe one can use it to understand heat and work. That approach certainly allows you to generate all the standard active dynamic equations that people have written down by other means. And I showed you two sets of results on polar and apolar confined fluids with surprises in both cases. I'll stop.
See, this pedagogical introduction that you sort of provided, that's at least at the level of a single motor, and it looks like what Magnusco introduced many years ago, 1993 or 94. Some people refer to it Magnusco's theorem, which says basically that you have a chemical coordinate, you have mechanical coordinate, you write exactly Langevin equations.
That was not new. That is the standard way of writing.
Then this is probably a generalization of that, because you are not...
It is, no, it starts precisely from that. What the paper I mentioned was Ulisher, Pro, and so forth. Revmont Phys 1990 something, 97 or something. It's the same approach.
But it is more than that, because you have...
It's descended from that approach, but it's applied to writing down active equations for collective variables on any scale. That's the...
So this gamma 1, 2 essentially is the coupling between the two, and that is responsible.
Gamma 1, 2 is the chemomechanical coupling. Yeah, it's exactly what it is. And the point is that if it depends on the coordinates in the system, then the coarse-grained dynamics of systems held in a stationary state by maintaining delta mu acquire terms that you would not be able to write down for dynamics about an equilibrium state. It just tells you what it means to say you can have terms there that weren't allowed before. Those terms are actually, it's odd. I mean, the point is the terms that you got by differentiating a free energy with respect to a coordinate, that has now become a coefficient, delta mu. And the terms that were a kinetic coefficient in the original description have now become terms which seem to stand at the same status as the existing terms of the equation. So it's a bit weird.
Sorry, maybe I missed your argument. So the conclusion, the polar case, super stable or super unstable, depends on what?
Depends on a coefficient which isn't the... Okay, so it comes from the following. Very sketchy. Yeah, so the difference between the polar and the apolar guys is that in the polar guys, you end up getting terms in the... Remember, this is in the confined, this is in dry, or this is under confinement, so momentum conservation is no longer an issue, and Galilean invariance is no longer an issue. So you can write down equations for P, which have terms proportional to V, right? And these terms come from... I think I have to write. These are actually very much like the terms we used to understand the flocking in the granular system that Ajay talked about. So, supposing you wrote down an equation for a bulk three-dimensional active system, a bulk three-dimensional system with a velocity field and an orientation field, then the orientation equation, even in the passive case, would have terms with 2 grads on V, right? Because a local, for instance, the local Poiseuille profile can orient in bulk. The velocity equation, because it's polar, will not only have terms with, like div of pi pj, but also terms with 2 grads on p, right? If you take this guy and look at the contribution from gradients in the confining direction and you z-average it, you will get terms just proportional to v in the p equation, right? If there's any kind of profile at all. So that's where these things come. This guy comes from that. So this is a kind of flow orientation coupling, but it's a flow orientation coupling of a type that you'll have only in a polar system, right? So that's where that coefficient, ultimately that's where that coefficient comes from. And this coefficient, the coupling of P, the way P produces a V, this has activity in it. This is active. And this has got hidden in my slide by my red handwriting. There's a coefficient here, little v, which is activity. So it's the point is therefore, it's a flow orientation coupling of particles, of structures with front-back asymmetry. So in fact, I think Bartolo and company comment on what that term means. Yeah.
If you say super unstable means what? What happens?
So I don't know what the final state is. So what I know is that, but I should actually say there's a connection between this and the granular flocking work that Ajay talked about. There also you have this PV type of dynamics. And we have been trying on the computer to engineer particles whose, remember, in the context of that work, you've got these granular rods with a front-back asymmetry. And what you'd like to know, I don't have that over here. But remember in that problem, if you directly wrote down the dynamics for a two-dimensional system, not worrying about incompressibility, okay? I have a polar order parameter field, I have a velocity field. Then a local polarization forces the velocity, a local velocity reorients the polarization, right? In this system, the interplay of these two coefficients can either destabilize the isotropic state to produce order or not, depending on the relative sign. So we tried to engineer particles which would perversely, in which a particle moving this way drags the fluid with it, but placed in a flow, a particle somehow perversely gets rotated the wrong way. We have been unable to do so. If you take, this is Rahul Gupta here? Rahul Gupta, one of my students, and Ronak, who is not here today, who's gone off to his PhD somewhere else. We tried to engineer, or these guys tried to engineer particles in which a flow in one direction a movement in one direction produces a flow in the same direction, but a flow turns the particle the wrong way. We've tried very hard to do it. It looks like if you pin the particle, you can make it turn that way. But if you let the particle move, this other state is an attractor. So I'm not actually sure if we can ever make super unstable. There's some piece of the particle scale mechanics, at least in the granular case, that always draws you into a situation where the interplay of flow and orientation always favors alignment. This is still work in progress, but I think we're reasonably sure of that. I don't know if the incompressibility constraint which operates in the stuff I've been discussing in this talk necessarily changes it. But that's roughly where it is. Yeah. These guys have tried everything. It's more like, I think the truth of the matter is the following. When you write these equations down, you say that this term is strictly active. A local polarization can't produce a forcing unless it's activity. This term, a flow producing reorienting particles, is perfectly permissible in passive systems. However, I think once you switch on activity, there's no guarantee that that coefficient has the value that it did in the passive case. You have to evaluate that coefficient for a motile particle. And I think that just changes things. That changes the kinematics, changes the mechanics of collisions of the moving particle with the beads in such a way that you just can't get this. Right? You see what I mean? I'm saying this term is allowed in a passive system. It's the minimal non-Galilean invariant flow orientation coupling for a polar system. It's allowed. But I think activity changes its character in some way. So maybe it's something deep, or maybe we are stupid. I don't know. I'd actually promised my students I wouldn't talk about the granular flock at all in this talk.
Any other questions? There aren't. Let's thank Sriram for a wonderful talk.